welcome to another episode of Physics Mania. Today I will be explaining a physics concept called the period of the pendulum. So, the period of the pendulum is the time it takes for a pendulum to swing once. And to put that into perspective, let's just quickly draw a pendulum right here. Length L, mass M. And let's say I drop it from point A. And here's point B. The period of the pendulum is from the time it travels from point A to point B and back again. That time is called the period of the pendulum. And there's an equation for this. And obviously it's called the equation for period of the pendulum. So let's just quickly write out that equation now that you know what the period of the pendulum is. So I'm actually just going to keep my pendulum right here off to the side. Let's give it some units, 4 meters and 15 kgs. And the equation is 2 pi not equals, I should put the time equals 2 pi times the square root of L over G. So we know what pi is, we know what L is, but you might be asking, well, what is G? G is the gravitational force pulling down, and approximately everywhere in the world it is about 9.8 meters per second. Well, you might be thinking, well, that doesn't make sense. Meters per second, what does that mean? That means if I drop something, it will take, after 1 second, it will gain 9.8 meters. It will go 9.8 meters per second. Then another second, it will gain another 9.8 meters per second. So after 1 second, it'll be 9.8 meters per second fast. And after another second, it will be 19.6 meters per second fast, as it gains speed every second. So now that we know what that is, as you might have noticed, if you haven't, the weight of the bob, this weight, is not in the equation. As you can see, the equation says that this could be 15,000 kgs, and the period of the pendulum would be the same. And I'll be explaining this at the end of the video. And what also doesn't make sense is that I could drop the pendulum from here and it will still be the same period. That doesn't make sense either, does it? Well, I'll be explaining it at the end of the video. You can skip there if you want. I will put a time mark in the description for it. In the meantime, I will write out this equation with the things that we know. Plug in the values that we know, like the length. That's the only value we need. Time equals 2. If you're going to solve this equation with me, I suggest you use the pi button on your calculator. But if you don't, you can always use just 3.14. I will be using the pi button because I have one. It's a little more exact. Times the square root of L, which is 4, over G, which is 9.8. And now you can solve this by yourself. The answer you should get, if you want to pause it right now and solve it, should be 4.014, rounded to the nearest thousandth. That's what I like to do in physics. A lot of other physicists like to round to the nearest hundredth. I don't like rounding to the nearest tenth. It's just not as accurate. Obviously, this decimal goes for a bit more, but I'm just going to round it for simplicity. And so what that means is that is the time it will take for this bob to travel. Let's move it here. For this bob to travel from point A to point B and back again. 4.014 seconds. But always in physics, what you must do is add an uncertainty. And let's make that 0.02 seconds. And what the uncertainty is, it gives you a little of room for error. If you want to try this, which I highly recommend, it is very fun doing physics experiments, then you will get somewhere between 4.012 seconds and 4.016 seconds. And that is because you always have to add an uncertainty. Maybe you're off on your timing a bit, or maybe you're just not fully exact on the exact length of the pendulum. And so that uncertainty gives you a little room for error. Obviously, we can never be perfect in physics, especially in physics. And now if you made it here, or if you're coming from the timestamp in the description, I will be explaining how the weight or degree of the pendulum does not affect the period of the pendulum. So let's say I'm dropping the pendulum from here, and here is the vertical length. Sorry, I can't draw dotted lines like Walter Lewin does, but I can draw a dotted line. And this is, let's say, 30 degrees. So, and it does not matter if I drop it from 90 degrees or 0.5 degrees, the period of the pendulum is the same. But why is that? And that is because if you drop it from, say, 90 degrees, obviously it will travel faster because there's more time for the kinetic energy to build up. But it goes hand in hand with having to travel a longer distance. While this pendulum has to travel, it will not gain as much speed as the 90-degree one, but it only has to travel this much. It does not have to travel the full length. And that's why the length, how far you pull it back, it does not matter. So don't worry. And I'll be explaining how the weight does not matter. So the weight does not matter because, let's draw 15 kgs. And ignoring the waist for now, 5 kgs. And this is because if you drop the pendulum from here, 15 kgs, obviously it will go faster coming down because the 9.8 meters per second, and it will speed up more because of the momentum it has. It will have a greater momentum because momentum and kinetic energy has the equation for mass, has mass in the equation, and that's why it will travel faster. Whereas this, it will not travel faster coming down, but here's the catch. Once the 15 kg pendulum reaches the bottom, reaches full kinetic energy, and starts going up again, 15 kgs is much heavier. It's much harder to pull up than 5 kgs. And so that's why it gains more speed coming down, but it has to carry more weight going up. And that's why it loses its kinetic energy much faster and regains its potential energy. And we know that it can never be higher than that, but it will actually be much lower than the 5, even though the period will be the same. So thank you for watching. I will be uploading a little more often. I'll try to upload maybe once or twice a month. And thank you for tuning in to this episode of Physics Mania. I hope you join us again. Thank you.